Hello everyone, I am Madhankumar and I'm going to present my final presentation for machine learning. And my topic is using deep reinforcement learning for stock market prediction. Let's get into it. So, the introduction, it introduced the stock trading environment, a custom gym environment for reinforcement learning. It uses historical stock data as example Apple's 1 year data to simulate stock trading. The agent learns to make a decision like buying, selling, or holding stock to maximize its portfolio value. And then dataset. So the dataset historical stock prices of Apple's 1 year data and pre-processing steps like calculate 10 days moving average as MA10 and calculate 20 days moving average as MA20 and then calculate volatility 10-day rolling standard deviation. Then deep Q learning as DQ1. So the DQ1 uses a neural network to approximate a Q value for state action pairs. It helps the agent choose decisions by evaluating their expected rewards. Like in reinforcement learning, a branch of machine learning, reinforcement learning is a subfield of machine learning where an agent learns to make sequel decision by interacting with an environment. Key concepts in reinforcement learning: agent, environment, action, state, and reward. So, agent, the learner or decision maker; environment, as where the agent operates; action, choice that agent can make. Example: buy, sell, hold in stock trading; state, current situation of the environment. Example: stock price, portfolio balance; and reward, feedback received after taking an action, positive for good decision and negative for bad one. In reinforcement learning, the agent's goal is to learn a policy, a strategy that maximize long-term reward through trial and error. And then DQ an agent. So the components: replay memory, stores experience, e-greedy, uh, and policy balance, exploration and exploitation, target network, stabilized learning. So DQ1 is a machine learning that falls under reinforcement learning. DQ1 use deep learning neural networks to handle large and complex environment where traditional reinforcement learning struggles. So machine learning provides the border framework. Reinforcement learning defines the decision-based learning structure, and DQ1 is a practical and scalable algorithm that applies deep learning to reinforcement learning problems like stock trading. So the neural network architecture for Q network. The Q network has three layers: input layer, hidden layer, and output layer. So each layer processes state information to predict Q values for each actions. And then experiment and implementation. Environment design. The trading environment simulates a daily stock market, updating the agent's portfolio based on the chosen action and providing rewards based on portfolio performance. The reward at each step is based on changes in portfolio value, encouraging actions that maximize long-term gains. So the neural network implementation. The DQ1 model is implemented in PyTorch using fully connected layers. With the following design, the deep Q network used in this study was designed to approximate the Q value function, which predicts the expected cumulative reward for each possible action in a given state. The DQ1 was implemented using PyTorch, a widely used deep learning framework that offers flexibility, dynamic computation graphs, and efficient training support. Then training the DQN agent. So the training process involves storing experience in memory sampling batches and updating the queue network through backpropagation. The process reset environment and select action using the eGreedy policy and store experience and training the model. So the agent was trained over multiple episodes, with each episode representing a complex traversal of the historical stock dataset. The training process began by resetting the environment at the start of each episode. The agent then selected action based on the eGreedy policy, balancing exploration and exploitation. Upon using an action, the environment returned the next state, the immediate reward, and a flag indicating whether the episode had ended. Each interaction, comprising the state, action, and reward, and next state, was stored in the replay memory for later use as illustrated. Uh, Illustrated training process of stock prediction using DQ1. So many batches of this stored experience were periodically sampled from the memory buffer to update the queue network. The network's weight were refined and backpropagation and gradient descent, minimizing a loss function that captured the difference between predicted Q value and target Q value obtained from the target network. To ensure training stability, the target network was updated at regular intervals. The training continued until all episodes were completed, with hyperparameter such as learning rate, batch size, and discount factor carefully turned to optimize performance and coverages. So then result. So the rewards trend graph shows how the agent's performance improves over episodes, indicating successful learning. So the upper upward trend demonstrates that the agent adapts to the environment, so making better trading decisions over time. The fluctuations in rewards reflects market volatility and exploration and exploitation. So the agent's total reward improved progressively across episodes, indicate successful learning. Reward fluctuation reflected the trade-off between exploration and exploitation as well as inherent market volatility. Graphical results from the training session showed an upward reward trend over episodes, improved trading decision as training progressed. So the performance was assessed based on cumulative portfolio value over episodes. Reward consistency across different training runs. Although basic DQ1 achieves a responsible performance, the results suggest the future improvement could be achieved by exploring more advanced algorithms like double DQ1 or incorporating additional market indicators. So future work. Explore advanced DRL algorithms like double DQ1, PPO, or dueling network for improved stability. Integrate sentiment analysis from news articles or social media to enhance market state representation. Extend the framework to multi-stock portfolio and real-time trading environment. So this study explored the application of deep reinforcement learning, specifically the DQ1 algorithm, to the problem of stock market prediction and trading strategy optimization. The goal was to develop a trading agent capable of learning effective buy, sell, and hold strategies by directly interacting with the simulated stock trading environment through careful system design including data pre-processing, custom environment step setup, DQ1 model construction, and rigorous training. The agent was successfully able to learn and improve its decision making progress over time. Thank you.